Our first example says, a commercial plane has been flying for 3 hours when a change in the wind decreased the plane's average speed by 30 kilometers per hour. If the entire trip of 2,540 kilometers took 5 hours, how far did the plane travel before the wind changed? I often like to draw pictures for these, and my students tell me that these drawings are terrible, so please bear with me. So I have a commercial airplane. It has wings, it has passenger, windows, and a cockpit there. Alright, so this plane is traveling, and the total distance that it goes is 2,540 kilometers, and it does that in 5 hours. Okay, I got those numbers here. 2,040 kilometers took 5 hours, and that says for the entire trip. So that is the entire length here that I'm putting in red. At the beginning of the trip, they traveled for 3 hours. Okay, they flew for 3 hours and then the wind changed. Okay, so for the first 3 hours, we actually don't know how fast they were traveling. So they were traveling some unknown kilometers per hour. Then, so that's the first 3 hours. Then for the last 2 hours, and I've done my scale terribly here, my apologies, 2 hours should look shorter than 3 hours. For the last 2 hours, okay, and I figured out 2 hours because I did 5 minus 3, they have to fly for another 2 hours, their speed decreased by 30 kilometers per hour. So now it's the previous speed minus 30, and we don't know the previous speed, we called that x. So x minus 30 kilometers per hour is the speed for the last 2 hours of the flight. So let's apply what we know about distance, rate, and time. For the first 3 hours, they flew some unknown distance. This is distance 1. I'm going to call that d sub 1 for distance 1. For the last 2 hours, they flew another distance, distance 2. The whole thing, 2,540 kilometers, I'm going to call that just d for the total distance. We know that the two unknown distances, d1 that they flew for the first 3 hours, plus d2 that they flew for the last 2 hours, has to add up to 2,540 kilometers, because that was the total distance that was traveled. So let's use that distance equals rate times time formula. The first distance, d1, was 3 hours of time at this unknown x rate. So the rate was x kilometers per hour, and the time was 3 hours. So here, the hours cancel, and we're left with 3 times x kilometers is the first distance. The second distance, d sub 2, has to again be rate times time. The rate in that case was x minus 30, and the time was 2 hours. So we have x minus 30 kilometers per hour times 2 hours. So again, the units of hours cancel, and we're left with, I'm going to write this as 2 times the quantity, x minus 30 kilometers. Notice again, we're using that distance equals rate times time formula, and I put the units in to help myself check that both of these came out in kilometers for my distance, and they did. So an expression for distance 1 is 3x kilometers, and an expression for distance 2 is 2 times x minus 30 kilometers. And we know that if we add those together, we should have a total of 2,540 kilometers. So now I have one equation with one variable, and I can go ahead and solve. So 3x plus, I'm going to distribute 2 inside the parentheses, so 2x minus 60 equals 2,540. Adding 60 to both sides, we get 2,600 on the right, because 40 plus 60 is another 100. And on the left, I'm going to combine these to say 5x, because 3x plus 2x will get us 5x. So 5 times x is 2,600. I'm going to divide by 5 on both sides. X comes out to be 520 kilometers per hour. Okay, I know that x is going to be a speed, right? Those were the units I already said that it should have. So x is 520 kilometers per hour, but that was not what we were asked to find. We were not asked to find its speed. We were asked to find the distance. How far did the plane travel before the wind changed? So at this point, from this point, how far did it travel? What is distance 1 is really what we were asked to find. So let's take distance 1 was 3 times x, and now we know that x is 520. So distance 1, let's see, well 3 times 500 is 1500, times 20 is 60, so 1,560 kilometers is distance 1. We can check this quickly by saying, okay, well then what was d2? d2 would have been 2 times whatever the original speed was minus 30. Well, the original speed was 520, so minus 30, 490. Okay, so 2 times 490 is going to be 980 kilometers. And we want to check and say, okay, well, is 1560 plus 980 equal to 2,540? Let's see. And in fact it is, yes. So the distances we found for D1 and D2 do add up to the total distance of 2,540, which means our answer here of that initial distance before the wind changed, being 1,560 kilometers, is our response for how far did the plane travel before the wind changed. Alright, this problem says a cargo ship must travel at an average speed of 25 kilometers per hour to make its 14-hour run on schedule. During the first 4 hours, bad weather forced the captain to reduce the speed to 20 kilometers per hour. What should the average speed of the ship be for the rest of the trip to keep on schedule? So we have a cargo ship, and it has to travel for a total of 14 hours at an average speed of 25 kilometers per hour. For the first 4 hours, the speed had to be 25 kilometers per hour because they had bad weather. So they went 4 hours, so they sailed for 4 hours at 20 kilometers per hour. Now the question is, for the last 10 hours, how fast do they need to travel to make up the time they lost earlier? So 10 hours at what speed? This is our unknown, x kilometers per hour. How fast do they need to travel to still make it there on time? Thankfully, we can calculate this first distance here, d1, because we have distance equals rate times time, and we know the rate. They were going 20 kilometers per hour. We know how long they traveled that fast. It was 4 hours. So the hours cancel. 20 times 4 is 80. So the first distance that they traveled through bad weather was 80 kilometers. Our unknown distance here, d2, they're going to go x kilometers per hour, and they're going to go for 10 hours. So I'm going to cross out the hours there. Distance 2 is going to be 10x kilometers. That's how far they need to travel, and x will be the unknown speed that they need to travel at. We need to know the total distance that the cargo ship needs to go. So the total distance, d, is going to be 25 kilometers per hour. That's the average rate that they need to achieve, times the 14 hours that they need to get there in. So crossing out the hours here, 25 times 14 comes out to 350. So the total distance that they need to travel is 350 kilometers. So again, we know that d1 plus d2 has to equal the total distance. So we know that 80 kilometers plus 10x kilometers has to add up to 350 kilometers. So we'll subtract 80 from both sides. On the right, we'll get 270. So equals 10x. Divide by 10 on both sides, we get that x equals 27. And we know that its units have to be kilometers per hour. So they have to travel 27 kilometers per hour to make up that distance. So they must average 27 kilometers per hour for the last 10 hours of the trip. And that will get them to travel the last 270 kilometers and meet their deadline of 14 hours. Our last example is a little bit different than the last two, so we're going to go through more of an explanation of the scenario before we solve the problem. A freight train traveling 100 miles an hour took 48 seconds to pass a motorcyclist going in the same direction at 40 miles per hour. Assuming the length of the motorcycle is negligible, find the length of the train. If the train and the motorcycle were traveling in opposite directions, find to the nearest second how long they would have taken to pass each other completely. We're going to ignore that last part for a second and just worry about the first question, figuring out the length of the train. So the first thing we know is that there's a freight train traveling at 100 miles per hour. This freight train is traveling at 100 miles per hour. So it's on some tracks next to a road, and on that road, there's a motorcyclist going 40 miles an hour. And at some point, the train passes this motorcyclist, and it takes 48 seconds to go past the motorcyclist. When they say here, assume the length of the motorcycle is negligible, that means that it's essentially very small compared to the length of this freight train, right? I imagine that this train goes off the screen here. So the train is much, much longer, okay, in comparison to the motorcycle, and we can essentially think of the motorcycle's length as practically zero. What we know is how long the train was, some part of the train was next to the motorcyclist. So that happened over a period of 48 seconds. When we think about two objects going in the same direction, but at different speeds, the train is going a certain speed relative to where the motorcyclist is. So if the motorcyclist here is going 40 miles an hour and the train is going 100 miles an hour, the train is going 60 miles an hour faster than the motorcyclist. So if we were going the same speed as the motorcyclist, it would look to us as if the train were going 60 miles an hour. What that means is that if we imagine that the motorcyclist actually was standing still and not moving, then by comparison, we're only thinking about the train going 60 miles an hour. So we can say that the rate of the train passing the cyclist, the motorcyclist, is 60 miles an hour. That is its rate of passing the motorcyclist. That's not the actual speed it's traveling along the earth, okay, but that is its speed in comparison to the motorcyclist. So if it took 48 seconds, okay, to pass the motorcyclist, then the distance that it took to do that is how long the train is. So we're looking for another distance equals rate times time problem here. Distance is our unknown. It's actually the length of the train. So I'm going to change that to L, the length of the train. The rate of the train in comparison to the motorcyclist, we said, is 60 miles per hour, and the time it takes to pass is 48 seconds. Now here we can't just do 60 times 48 and be done with it, because seconds and hours are different units, so we need to do a little bit of a switcheroo. We need to make sure that we convert seconds to hours, so 48 seconds, okay, we need to change that to hours. We need to have hours in the numerator and seconds in the denominator. Well, how many seconds are in an hour? There are 60 seconds in each minute, and there are 60 minutes in an hour. So 60 times 60 is 3,600. So there are 3,600 seconds in 1 hour. So the length of our train is going to come out to be in miles because hours are going to cancel here, seconds are going to cancel here. 60 times 48 and then divided by 3,600 comes out to 0.8 miles, 8/10 of a mile. That is the length of the train. The second part of the question asked us how long it would take for the train and motorcyclist to completely pass each other if they were moving in opposite directions. So now, let's suppose our train is going in the same direction. It's still going 100 miles per hour. And now the motorcyclist is moving in the opposite direction at 40 miles an hour. So before, when we were talking about the train's speed relative to the motorcyclist, we subtracted the 40 miles an hour away because they were going in the same direction. This time we're going to add the motorcyclist's speed. They're going to pass each other faster this time because now we're going to add 100 miles an hour to 40 miles an hour. So now the rate of the train relative to the motorcyclist is 140 miles an hour. We know that the length of the train is 8/10 of a mile, so that's the distance that they need to travel to pass each other. So we know that the distance is 8/10 of a mile, the relative speed is 140 miles per hour, and we want to know the unknown amount of time it's going to take for them to pass each other now that they're going in opposite directions. When the train was passing the motorcyclist, it took 48 seconds. This is going to happen even faster because it's the same distance that they're going, but now their relative speed of the train is much faster than it was before. So I know that my answer is going to be less than 48 seconds, which means I probably don't want to solve for it in terms of hours like I would be doing here with miles and miles per hour. So what I'm going to do first is I'm going to change 140 miles per hour into miles per second. So this is 140 miles per 1 hour. And we know from earlier that 1 hour is 3,600 seconds. So here, 140 and 3,600 are both divisible by 20. 140 divided by 20 is 7, and 3,600 divided by 20 is 180. So now we know that this 8/10 of a mile, okay, is equal to a rate of 7 miles in 180 seconds times our unknown number of seconds that we're trying to solve for. So if I want to clear that fraction, that rate on both sides, I can multiply by 180 seconds divided by 7 miles. Okay, I'm multiplying by the reciprocal to clear this fraction away. So on the left-hand side, we're doing 180 seconds times over 7 miles times 8/10 of a mile. So 180 sevenths times 8/10, we will get 18 times 8 divided by 7, which gets us 20.5714 ... seconds is equal to x. And we'll round that to the nearest second because that's what the problem asked us to do. So 21 seconds is the time it takes them to pass each other if they are going in opposite directions.